Okay, so we're now going to look at some basic trigonometric derivatives, and I want to begin here by actually looking at the graph of sine of x and cosine of x. Okay, so notice, first of all, these are in terms of radians. So in order for these shortcut rules to work, we do have to do the derivative in terms of radians. And so what I want you to notice here is that for the sine of x, let's look at the tangent lines. Okay, so first of all, notice that these have a horizontal tangent line at each of these points, don't they? Right? And if you notice here, these are actually the points where cosine crosses the axis. So those are the points where cosine is equal to 0, right? So the derivative of sine of x is equal to 0 at the same place the cosines are equal to 0. Okay, now if you look at this place, this point here, or this point here, the slope of this line is actually almost like 1. It doesn't look like it here because this is much bigger than that, and it goes up much higher. But if these scales were the same, then the line, or the graph of sine of x and y equals x are like almost identical right around that point. So what it means is at this point, sine, the slope of the sine is 1, just like the cosine is. At this point, it's negative 1, just like the cosine is. Okay? And so on. Over here, it's negative 1. Up here, it's 1. And so what I'm trying to show here is it looks like the sine here, when it's 0 and when it's 1, is when the cosine is 0 and 1. Or where the slopes are 1 and 0, or slope is 1, 0, negative 1, 0. Well, cosine is 1, 0, negative 1, 0. And so it looks a lot like the derivative of the sine here is equal to the cosine. And that is actually the case. So one rule that we get is that the derivative of the sine of x is equal to the cosine x. Okay? And you can kind of tell by looking at the slopes of these compared to this graph. Okay? Well, what about the derivative of cosine of x? Well, at 1, it is equal to 0, just like sine is equal to 0, right? But then as we go from here to here, the slopes are negative, and at this point it would be negative 1, but sine is positive 1, right? So the slopes here, being negative, are not the same as the sine, because these are positive, okay? But if you go the other way, like this, so in other words, if you take the opposite of sine, then the same thing happens as before. In other words, what I'm trying to say here is that the derivative of cosine, it's not equal to sine. I guess that would have been kind of nice, but it is equal to the opposite of the sine of x. And these are the two main derivatives, the derivatives for sine and cosine. So the derivative of sine of x is the cosine of x. The derivative of the cosine of x is the opposite of the sine of x. Okay? And so now let's use these to find some derivatives here. So if I want to find the derivative of this, dy dx, okay, this is a constant multiple, negative 3, but then the cosine of x is negative sine, so the negative sign would cancel out that 3, giving me just 3 sine x, and then the plus 10, that plus 10 just goes away, and so that would be the derivative. Okay, I suppose I could have broken this down a little bit more like this, d dx, or dy dx. I could have done the constant multiple rule, the opposite of the cosine is the opposite of sine of x, and then the derivative of 10 is just 0, and then this would have been 3 sine of x. That might have made it a little more clear. But since the constant multiple is negative and the derivative of cosine is the opposite of sine, then together they become positive 3 sine x. Okay, so what about this one here? Well, first of all, we could split this up over a common denominator. This would be like 3/5 x squared minus 1/5 sine of x. Okay, and then f prime of x, I could do the power rule, bring the 2 down, and I would get 6/5 x, and then minus 1/5, that's just constant multiple rule, times the sine of x, and the derivative of the sine of x is just cosine x. So it looks like I would get that. Okay, now what about this? Well, we're just going to we're going to break it up over the sum and pull out the constant multiples, so that the derivative of f of x would be, for sine it's cosine, so it would be 8 cosine x, but for cosine it's opposite sine, so this would be plus 3 sine of x. So that's what I would get. And then this one here, well, let's see if we can do this one. We may not even be able to do this one. So I could break this up. This would give me 5x over square root of x, which is, let me just write x to the 1/2. Okay, this would be minus 3 cosine x over x to the 1/2. Okay, well this I could simplify. This would give me 5x to the 1/2 minus, this would be 3 cosine x, x to the 1/2. Okay, now don't make the mistake here. I could take the derivative of the first piece, no problem. But this piece here, we don't know how to take the derivative of. And the reason is because we cannot just take the derivative of the top and the bottom. So it's not like a limit where the limit of the quotient is the quotient of the limits. The derivative has a more complicated quotient rule. Okay, so in other words, d dx of f of x over g of x does not equal f prime of x over g prime of x. Okay, and similarly, d dx of f of x g of x does not equal f prime of x g prime of x. These are not equal. Okay, you need a product rule and a quotient rule to find these. Okay, we won't learn about those until some later videos. So this last one we're not able to do. Okay, well, there are actually shortcut rules then for all 6 derivatives. And what I would do is make sure I would at least commit to memory these 3. Okay, the first 3. And then, you know, you could always look up these. And there's kind of a patterns here, relationships. But basically, for sine, the derivative of sine of x is cosine x. For cosine x, it's opposite sine x. For tangent of x, it's actually secant squared x. Okay? For cosecant x, this is kind of strange. It's the opposite of cosecant x times cotangent x. And for secant x, it's secant x times tangent x. So this is kind of weird because the derivative of secant x is secant x times tangent of x. So the function itself is included in the derivative along with tangent of x. Same with this cosecant, but you have the opposite cosecant times cotangent x. And then the derivative of cotangent of x is the opposite of the cosecant squared of x. Kind of like derivative of tangent is secant squared. Derivative of cotangent is opposite cosecant squared x. Okay, so these are all the derivatives for all 6 functions. So let's see if we can use them here. So to find this derivative, maybe I'll write them over here. F prime of x. For tangent, we get the secant squared x. For cotangent, it's the opposite of the cosecant squared x. So the derivative of this is equal to that. Okay. So what about this? F prime of x. For secant, it's secant x tangent x minus, and then here, this is, I can use a power rule. So in other words, I can break it up over this, and then I can use the power rule. So I would be having x to the 1/2, I'd be taking the 1/2 down, and then I'd subtract -1 from the 1/2 exponent, and I would get x to the -1/2. Okay, and I could just keep it like that, or I could bring that down to the bottom and put it in a radical. Okay, I'll just keep it like that. And then f prime of x here, 3 cosine of x, that's just the -3 sine x, because cosine x is negative sine x. And then this, for -2 cosecant x, cosecant x is negative cosecant x cotangent x. So the negative here will make that positive. This is a constant multiple. And then I'll have cosecant x cotangent x. So that would be the derivative of this. Okay, so some of those other rules are a little strange, especially because they involve this product of two trig functions. And these are the square. But that is what the derivatives are. So they just happen to be that. So, okay, so those are the derivatives, kind of the basic derivative shortcut rules for the trigonometric functions.